Okay, so we have Martha Grover with us, and she fortunately is able to present from home today because of the Georgia Tech is shut down, and so we're glad to have her here. Let me just cover a little bit of her biography. Martha, she's an associate professor in the School of Chemical and Biomolecular Engineering at Georgia Tech. She got her undergraduate from University of Illinois, Urbana-Champaign, and MS and PhD from Caltech. And she's been at Georgia Tech since 2002. She's received a number of very prestigious awards, including the Career Award in 2004. 2011, she received the Outstanding Young Researcher Award from the CAS division at AITHE. So she's done some amazing work with very multi-scale systems and feedback control, applying control theory and optimization techniques in places that a lot of us never really even dreamed of. And we're excited to hear some of the things that she's going to be presenting today. And I will go ahead and just turn it over to Martha. And in doing that too, I'll just mention these webinars. We like to have them interactive. So, Martha, I warned her about this before, but she can expect to get interrupted many times during the presentation. So feel free to, if you have a question as we go, that feel free to interrupt with a a comment or unmute your microphone. And then one thing is Martha is sharing her desktop. The other thing that I'll ask you to do is just go ahead and put your name, affiliation, and some of the things that you're working with in the chat window. And I'll go ahead and do that as well. We'll just try to keep our chat windows open, to be able to have the discussion there on the chat as well. And Martha, I'll just ask that you keep your chat window open too, if you can. And,
okay, so just have it on the edge or something.
Yeah, just have it on the open, and then we'll try to field any questions as they come in.
Okay.
So go ahead and click share my desktop for yourself, and you should be able to open up and start sharing.
So share my desktop. There it is. Okay, and let me open up my chat, and then slideshow. Does that look good?
Looks great.
Okay, so yeah, definitely welcome questions. It'd be great to have this be interactive. This is a pretty interdisciplinary topic, so I'll try to make it accessible, but I'll probably leave out some important details that you're thinking, wondering something. So please definitely ask for those kinds of clarification questions. This is based on a collaborative project with a former postdoc of mine, Yudun Xu, who's now at Halliburton and working in the controls group there, and a graduate student, Shun Tong. And then we're also collaborating very closely with Mike Bevan's group at Johns Hopkins, and as well as with David Ford at University of Massachusetts. Let's see, it's not advancing. Is there any reason why that would not be advancing because of?
No, I don't think so. I think.
Okay, well, I just clicked on it, so.
Okay.
Okay, we'll see how it goes. So really, I have been interested over my research career, maybe 15 years, in problems of self-assembly, controlling self-assembly, and really focusing on problems where the dynamics, the kinetics are important, such that we can't just predict the structure based on purely equilibrium considerations and models. And that means that the process really determines the final structure of the material. Now, most of the systems that I have been looking at prior to this colloidal assembly problem have been smaller, looking at small molecules or atoms assembling. But one of the really great things about this project from a controls perspective is that the particles are still small enough to be stochastic, to be a good model system for self-assembly broadly, but they're also large enough that we can see them under a microscope. And these particles are 3 microns in diameter, and that's large enough to see. And really, visualization and characterization techniques are getting better and better, such that we can start to go below 1 micron into nanometer sorts of scales and still see particles. We can't see them so well down at the angstrom to nanometer scale, but techniques are improving as well. So I think there's a lot of potential in terms of sensing. So these colloidal particles, which really just means micron-sized particles, have been used within the physics community also as kind of a model system for understanding self-assembly because they're a little bit larger than atoms or molecules, but they also are of practical importance. Recently, they've been proposed under the name of metamaterials, in which these colloid particles assemble into crystals, regular crystals, and they have really interesting optical properties. So they can be used for optoelectronic applications, so to make circuits out of light, and that's much faster with lower losses. But also they've been proposed for materials like cloaking and stealth materials where you could become invisible, so all sorts of really wild applications. But you need to make them in a very ordered array, and that turns out to be pretty difficult. Even though the thermodynamic minimum is that ordered state, when you try to process them, you get defects. And so you can see that in this figure. This figure is from my collaborator's lab, Michael Bevan's lab. And what he's looking at here are different numbers of particles assembled under the same voltage, which drives the interactions in assembly. And you can see for the smaller systems, it's a very ordered array, but as you go larger and larger, you start to get these defects in the crystals. And so even 304 particles, that's really a pretty small system from a practical application, but you can still see here that these multiple grain boundaries are forming under this particular voltage. So an alternative to applying a voltage and just letting all of the particles move under that voltage would be to individually place the atoms using something like an atomic probe, but that's just not really practical from a scale-up point of view. And so that's why we're interested in self-assembly from a processing and manufacturing point of view. So if we waited a very, very long period of time, eventually the system would go to its thermodynamic minimum, which would be the crystalline state. So say in the A panel, those grain boundaries would eventually migrate out of the crystal. But it would take a very long time. So again, from a processing point of view, that's not really what we want to do. We want to rapidly assemble defect-free materials. And we're going to change external potentials like voltage or temperature, which influence the particles, but it's a highly underactuated system. We have many, many particles and only a small number of process inputs or manipulated variables. And so in the self-assembly field, there's this trade-off between assembling slowly and getting an ordered state and assembling quickly but getting getting more defects. And so the idea really is that by having feedback control, we can get around that sort of what's seemingly kind of a fundamental limitation. By seeding defects, we can go in and target them and heal them and then carry on with the process. So I think from that point of view, it's a really exciting opportunity for feedback control that we could really address this current limitation in self-assembly. So here are some pictures for the particular experiment that I'm going to be talking about today in Mike Bevan's lab at Johns Hopkins. He's also in chemical engineering, chemical and biomolecular engineering at Johns Hopkins. And the idea is that you have an electrode. It's called a quadrupole electrode in that upper figure because there are 4 different arms on the electrode. And you apply an AC field, and the field exerts forces on the particles, and then the particles interact with each other as well. So these are silica particles that we're looking at. In this particular figure is 130 silica particles, about 3 microns in diameter, and they're in water. And under the particular configuration I'm going to talk about, we keep the voltages low enough such that the particles stay in the plane, and that way we can view them with standard optical microscopy. If we put the voltage up higher, they'll form 3-dimensional structures, and these also can be visualized using confocal microscopy, but it's not as fast and it's more complicated. It is something that the Bevan lab also does, but I'm just going to talk about 2D assembly today. Another key feature of the system is that by restricting our system and actuators to weak interactions, these assemblies are reversible. And that's not always true in particle or colloidal assembly, but here it's reversible. So that's important in that if we make a defect, we can pull it apart again. So that's just sort of a clarification in case you have some familiarity with these kinds of systems, but think of them as being irreversible.
So Mark, a quick question about this. Now this is, I guess, used in pharmaceutical manufacture, is that right?
No, not really. Not really. It's used for making optical materials. Now, crystal growth is pretty important in pharmaceutical applications, and so that's a similar sort of phenomenon, but at a smaller length scale. But from a theoretical and modeling perspective, this would also be relevant there.
Okay, so optical applications. What kind of optical applications would something like this be targeted for?
So you can transmit light with very low losses. So in terms of communications and really just replacing electrical circuits with light-based circuits and communications.
Interesting. Okay.
Hey, Martha.
Yes.
How large that electrode assembly that's shown in the upper right corner? What's the size scale of that?
So it's pretty macroscopic. There are some screws there and some wires. That is not under a microscope.
Okay.
But the lower image, that is in a microfluidic device that's placed in the center of those electrodes, and that is under the microscope.
Okay.
And in that case, the particles are 3 microns.
Okay, great. Thanks.
Okay. Yeah, it'd be nice to just have scale bars on there. But the upper one really is macroscopic, but it contains the lower microscopic one.
Okay.
Other questions while we're chatting? Oh, so I see the chat window here. What is the mechanism for the electric field to exert force? So I think in the next slide I'll get into that a little bit more. So hopefully, if you still have questions, do that. But by changing the frequency of the AC field, we can actually change from being attractive to repulsive. And then the final point here down below is that we have real-time monitoring with optical video microscopy, and have been using image processing to extract all the particle locations. So we really do have a lot of real-time information about the system. A frequency of about a second is for the image processing in a system. So we're really viewing this system in terms of classical mechanics to describe the particle motion. In this particular quadrupole assembly system, the particle field interactions are really dominant. There are also particle-particle interactions, but the particle field actions are very important. There's an induced dipole on the system. Dielectrophoresis is another word for that, because of the inhomogeneous electric field that is created by this electrode geometry. And so this upper figure shows an example of the electric field or electric potential, how that's calculated based on the geometry of the electrodes. If the electrodes were at the lower, or 2 electrodes at the lower boundary, then you can calculate through electrostatics what the electric field would be, and from that compute the dielectrophoretic force. So that's part of the modeling that I'll talk about in a little bit. But dielectrophoresis is really a driver here, which comes from the AC electric field. But then there are also particle-particle interactions, electrostatic interactions. These particles are charged, and also dipole-dipole interactions that come from the AC, induced by the AC field. And then in addition, there are random forces here, Brownian motion on the particles. They're small enough that they do undergo Brownian motion, and so in terms of understanding broadly the ability to apply feedback control to self-assembly processes of microscale systems, that's really a key feature of the system. That it's not a deterministic system. But having defined these forces, one can then integrate the equations of motion for each particle in the system. And this particular study that I cited below by the Bevin group formulates a model based on geometry of the system, material properties, but there aren't really any fitted parameters. They did fit a few parameters that were measured based on geometry and concluded that the best fits were close to the geometric values. But for the most part, these forces can be modeled, can be understood and quantified. So here's the overall feedback control system that we're going to be talking about today. on the right is our process, the colloidal assembly process that we were just talking about. Then the sensor is optical video microscopy, and plus the image processing that allows us to get all of the particle positions at a frequency at a period sampling time of about 1 second. Then there's the controller, of course, that's going to help us get to hopefully get to a more desired structure, which in this case is really a more ordered crystalline structure. And then the controller is going to command the voltage, that AC voltage, to the quadrupole. So it's just in this case, just one manipulated variable. But it does change the electric field in an inhomogeneous way throughout the entire domain. I just wanted to show these figures. I did mention already some of these issues a little bit, that by changing the frequency of the AC field, we can change the direction of the force on particles. And a modeling approach that the Bevin and Ford groups have taken over the years is to model the, to first consider the forces on particles. So the two plots on the left are corresponding to the energy, the potential on a particular particle. And if you're in the middle of the domain, in the middle of the quadrupole, then at 1 megahertz, that's going to be the low energy state. So you're going to be driven to that. Whereas at 0.1 megahertz, the particle in the middle is going to be at the higher energy state. It's going to want to move out. But an alternative way to model the system that we can really think about in terms of state reduction is defining a small number of order parameters in physics language, or reduced state representation in control language. And in this case, in this particular study in which feedback control was applied, I'm going to talk about that on the next slide, they use this parameter called C6, which is a measure of how many neighbors an atom has in the crystal lattice. In the 2D crystal, it would be a hexagonal crystal, so 6 would be the maximum number. And so what the Bevin group had done is to compute the free energy of the system as a function of this one order parameter. So not the free energy associated with one particle, but with the entire ensemble, the entire system, and to characterize that energy as a function of this one coordinate, C6. And then they calculate those free energy profiles for different voltages to the system. And what you can see is that as you increase the voltage, the average C6 value increases. So as we push harder on the system, it crystallizes. Also, these wells are pretty simple in shape. They're kind of parabolic, and they have one minimum. So what that's saying is that in this particular system, that there aren't really kinetic traps or anything that we would get stuck in, that we can really kind of just drive the system maybe along that free energy minimum by slowly cranking up the voltage, for example. Now, this corresponds to a system that has 130 particles, and it has a pretty low salt concentration, which means that the charge effects of the particles are pretty significant. So the particles all have the same charge and they repel each other, and that makes it harder to form defects. So this is a simpler system. Then I'm going to talk about what happens when we raise the salt concentration and we get more defects. But that's in this particular case, it's hard to get defects in the system. The Bevin group had applied proportional control to this system. So this is before I got involved in the collaboration. So that's really one great thing for me about this collaboration, is that they had already interfaced all of their hardware and everything into MATLAB real-time workshop, and they had closed the loop already. The reason I got involved is that I was talking with Mike, and he was asking me, well, what should the control law be? So they had applied this proportional control law, but it didn't do everything that they wanted it to do, and that's not their area of expertise. But what they did is they applied a proportional control. If the system was above the set point, then they would want to, crank up the voltage. If it was below, then they would want to pull it apart. And so they actually used these two different frequencies in order to be able to pull in two different directions. But basically, it's a proportional control law, and they stepped up the system in crystallinity by increasing the set point in steps, and then they stepped back down again. So what you can see on the lower plot in green is that the voltage was kind of cranked up for the assembly, and then down again for the disassembly. But you can also see the orange plot corresponding to the right axis corresponds to which frequency they were using. So as they were assembling, they always used the attractive frequency, but as they were disassembling, they flipped back and forth between the attractive input and the repulsive input in order to not overshoot or undershoot their set point. So let me just show you some movies. This is during the assembly process under closed loop. And that C6 parameter is increasing. That's shown in the upper left. The radius of gyration is the measure of condensation of the system. So that's decreasing as the system is becoming more condensed. And then the voltage is also increasing. So then if we watch the disassembly process, let's see, that's assembly. See if I can go forward. There we go. The disassembly process, we start with the ordered state. It's very condensed in terms of RG, and then it's becoming less and less condensed. And the voltage is really flipping around kind of all over the place, and also changing even between those two frequencies, which is not shown in this movie. Okay, so that was a proportional controller, but if we really want to take some kind of optimal action, we really need a model for the system that we can use as the basis for our controller design. And here, again, we started working with the Bevan group on the models that they had already developed and to formulate those in a more control-oriented way. But they do have a Brownian dynamic simulation, which I already described a little bit, but in words it's just that should be d squared x dt for the acceleration. It's classical equations of motion. And then we have all these different forces. Sometimes fluid drag forces are included, and then it's called Stochastic dynamics, although typically that's not what we have been using neglecting drag forces, but we have Brownian motion forces, and we have all these external field-driven forces from the voltage. But this is very high-dimensional, nonlinear, and stochastic. So we have 2 or 3 coordinates for each particle, and we have, say, 130 particles. And we really don't want to control the location of each particle. Really, in terms of our control objective, the particles are indistinguishable. What we really want to do is control these average crystallinity metrics. So then the question is, well, can we come up with a lower dimensional model in terms of the properties that we really do care about? So a framework for doing that is Langevin dynamics, in which we have some reduced order coordinates that parameterize the manifold in which the system is evolving. And then one can describe the free energy of the system, which is W, and I showed that earlier on those free energy profiles. So that can be estimated from the Brownian dynamic simulation, from simulation data, as well as the drift, as well as the diffusion coefficient, which then represents how mobile or fluctuating the system is at various values of the order parameter. So if you can identify those spatially dependent coefficients in terms of your order parameters, then you have a reduced order model for the system. And so this comparison in the lower right is between Brownian dynamics and the Langevin dynamics model in terms of seeing how long it takes the system to pass certain points in the space, and that the comparison between the Brownian dynamics and the Langevin equation is pretty good. It's pretty good. Then you might also be asking, well, how do we figure out how to parameterize this low dimensional manifold if in fact it even exists? And this has been something that we've been working on with David Ford at UMass, who's been a longtime collaborator of my 7th as well. And they've used diffusion mapping, which was is a method that Koisman has worked on quite a bit, that Jan Kavakidis has been working on, and it's a manifold learning technique. And really what it helps you do is to take your high-dimensional data, like from the experiment or from Brownian dynamics model, and then to look for the dimensionality of the system. It doesn't tell you really what the coordinates are, but it suggests what the dimensionality of the system would be. And then the approach that we've been taking is to then just pose our own order parameters. We say, well, we need 2, so here are 2 that we know have pretty different information, are sort of orthogonal in some conceptual sense, and then to just go ahead and use them and build the Langevin equation from the Brownian dynamics equation. So in this case, we're using the radius of gyration, that condensation metric, which tells you how condensed the system is, but it doesn't tell you how ordered it is. So that's important, but it's not everything. So then we also need another metric, either C6 that I already showed you, average number of neighbors in the crystal lattice, or this other version of it we call psi6, that is a little bit more sensitive to when you have a small number of defects in a larger crystal. It provides a more sensitive measure. It really emphasizes those defects. And so that's turned out to be a better metric for us going forward. But again, it's capturing the orientation of the particle neighbors. So we have done a little bit of work in model predictive control. We have an ACC paper on that. I know there was someone on the call who works in model predictive control. But what I'm really going to talk about today is dynamic programming. the model predictive control, the computational demands were pretty significant, and we've had good success with dynamic programming. So I think going forward, that's really what we're focusing on, but we've gotten similar trajectories and performance for model predictive control and dynamic programming, and we may revisit model predictive control again in the future. We had kind of a naive interpretation or implementation of it in terms of computing averages, expectations based on sampling from the stochastic simulations. So that wasn't, I think there's plenty of room for improvement in the implementation of model predictive control. But here I'm going to talk about the Markov decision process. The idea here is that we're going to implement dynamic programming by describing our system dynamics in terms of a discrete state stochastic model, or Markov chain. And that's something that we've been using in my group really for a long time to approximate kinetic Monte Carlo simulations, so it was a very natural direction for us to take in that sense. But we run simulations of either the Langevin Equation or the Brownian dynamic simulation, and we use that to identify what's the probability of going from one discrete state to another, where the discrete states are still represented in terms of order parameters. So here, RG and psi-6 are the two that we use for our two-dimensional model. We also discretize the voltage space. Here we consider 6 different voltage levels that are representative of the range of particle interactions. And here we're computing, we have to decide how we're going to discretize the state. We have to decide what the time step should be. And that actually turns out to be pretty important in terms of having a Markov chain model that's going to accurately represent the Langevin dynamics or the Brownian dynamics simulation. But I think we've converged on a good combination of those. So for our objective function, we define a reward. And the reward here is just to maximize psi steps, so to have the highest crystallinity possible. And then we have a discount factor. Here, these equations are for the infinite horizon Markov decision process, but I'll show you some results for a finite decision process also. And we solve this with policy iteration. We solve for the control policy using policy iteration. So first I want to come back to that one-dimensional case and show you some results. This is for the case where the particles really repel each other, and so they tend to not form grain boundaries. So again, we've posed this kind of simple model of the system where we have these parabolic free energy wells associated with the system at different values of the voltage, which we call U here for the control input. So at low voltage, the system has a low crystallinity at long time, whereas at the highest voltage, it has a high crystallinity at long time. And then we just have sort of intermediate monotonic behavior in between. The diffusivity of the system that goes into that Langevin equation. Also, you'll notice it peaks at the free energy minimum for each voltage. So those extremum always correspond. So the system is much more mobile and diffusing when it's near its free energy. It's fluctuating a lot at the bottom of that well, and then it's not as mobile away from that. And so that turns out to be important in our optimal control policy. So this is a paper that was just published very, very recently from our group in transaction time control systems technology. So if you're interested in reading more and just seeing the methods, and this paper really documents all of that. So that's the paper to check out. We haven't published on the two-dimensional case, so I'll talk about it next. And we can also just follow trajectories of the system. What we see is the system and it comes up at first under each voltage, constant voltage, and then levels off at some constant value associated with the minimum of the free energy. So when we compute the optimal policy using the dynamic programming, we can apply actually different objective functions. So in the first one, we have no penalty on control action, so we're just trying to maximize C6, maximize crystallinity. And we have here a time, this is a finite horizon policy, we want to get there in 80 time steps. And the time step here is 1 second. So what we can see is that when X, our state C6, is low, then we should apply actually a high voltage to really drive the system quickly together. But then we need to back off, and actually it goes to these blue very low values. So then we need to back off and then slowly ramp up again. So you can see that in the lower plots for the blue curve, design 1 is the no penalty case. And so the system is just kind of slowly going up to the maximum value of 5 in 80 time steps. And if you look at the input trajectory, it starts high, goes very low, and then comes back up again. And on the right are the average over 1,000 realizations. So, but it shows conceptually the same sort of behavior, just with less noise. Now, if instead, yeah.
Okay, so could you? This is the one-dimensional case. So, so the independent, C6 is the only parameter that you're controlling here. You're not controlling radius of gyration. Is that right?
That's correct. And what we see in the Brownian dynamics is that the system evolves in the RG-C6 space along a one-dimensional manifold.
Okay.
So really, either RG or C6 could have been chosen here for the coordinate, and they should give the same behavior.
And roughly, how many states do you have here? How discretized is C6?
I think it's something like 0.1, so maybe something like 60 states.
Okay, great, thanks.
We have, in the two-dimensional case, I have shown here that we have a 50 nanometer discretization here. It's about 100 by 100 for the two-dimensional case.
Okay.
So about 100,000 states, and we have no problem computing the optimal policy.
For 10,000 states?
100,000.
Okay, great.
10,000. 10,000. Yeah. 10,000.
Okay, great. Thanks.
But we really, I mean, cursive dimensionality and all that. I've never done dynamic programming before, but really, it just solves it really fast, and then you just have a table lookup.
Yeah, that's my experience too. Is for that scale problem, it's not too bad. 100,000 is impressive. As you get to a million or more, it gets harder. But this looks very feasible, very intriguing.
Yeah. I mean, we thought this is funded by an NSF CDI, Cyber-Enabled Discovery and Innovation Program, and we were saying how hard it's going to be computational. Right. And there are a lot of challenges. We're dealing with large data sets and image processing, all those sorts of things, but really, so far, it hasn't, the dynamic programming part has not been complicated.
Okay, great. Thanks a lot.
Yeah, thank you for asking that. And another thing you might notice about this policy on the left is, even though it's time dependent, it's almost time invariant. So it almost doesn't change as a function of time. But if we add the penalty to the input, we say, well, we want, I don't know, minimize power or something. Not that that's so important in our experiment, but then we do get a time dependent policy where early on, if you're just trying to get to a high C6 at the end, it doesn't really help you too much at the beginning. And so you can see this colorful region here corresponds pretty closely to the no penalty policy. But then in all the other regions, you might as well just keep the input low. So of course we can tune, we picked a particular weight between on the penalty in this case to get some intermediate sort of behavior. But anyway, we can still get pretty good behavior in this design 2 case, which is the one with the penalty. We don't get quite as high here with this particular penalty, but we still get relatively high crystallinity, and it's still going up, of course. So it's not that he's saturated or anything, but anyway, it's just another ability to tune another way to tune the policy. And then we compared that against the case with the highest voltage, which is the only voltage that would allow you to get that highest value of C6. And so that's just slower, right? So we can just get there faster by using this time varying policy. Okay, but now I'd like to move on to the 2-dimensional case in which we do get grain boundaries forming. So it's a different salt concentration that promotes grain boundary formation or enables grain boundary formation through defects because the particles are not so repulsive. And so now we have RG on the vertical axis and Psi6 on the horizontal axis. And what I plotted here are trajectories under different constant inputs over that range that I talked about, 0.3 up until 1. And so really we need a high value of the voltage to really drive the system to this lower right quadrant, which is where we want to be. Now on the to really both condense the system and then drive ordering over to the right. Now the policy is shown on the right, and this is a time-independent policy, infinite horizon policy. So the policy is not time-dependent. So now you're at a particular value of RG and Psi6. You look it up. You get it from your microscopy image, and then you look up where am I on this table, and that tells you what the policy should be. So here the policies are numbered from 1 to 6. instead of being, numbered according to the voltage of 0.3 up until 1. But there are 6 levels here, and that's what we're looking at in the policy table. So basically what this says is either go high or go low. There's only a few places where you want intermediate voltages. That's because you're close to the assembled structure, so I think of that as, okay, don't just totally take your foot off the gas, or don't totally, put the pedal to the metal. So you need to have a little bit more subtlety once you get closer to the ordered state. But otherwise, what happens is we come down from the fluid-like state, and under about half of the trajectories, we actually can just sort of cruise over here and get to the ordered state with this just the highest voltage. But in the other half of the cases, we start getting into these situations where the system is condensed but not very ordered. So grain boundaries are forming. And when that happens, then we take our foot off the gas and we go to the lowest voltage that's in our action space, which is the blue region, and then that allows us to then come back up and allow us to come down here for more. Maybe we need to then take another corrective action. So the behavior of the system under the closed loop is shown here on the left. The Langevin dynamics and the Markov chain model predictions agree very well. When we implement the policy in the Brownian dynamic simulation, it doesn't agree as well. I'm going to show you there are some failed cases. I don't know, completely failed, but over this particular time here that we're considering, which is 300 seconds, there are some cases where the defects are not completely healed, and so that brings the averages way back. So that's in about 8% of the cases we get this happening. And so this is just another view. It's looking versus time over the 300-second trajectory shown here. So you can see that for the Markov chain Monte Carlo and the Langevin dynamics, they still don't completely agree in terms of how many corrective actions need to be taken. We see more cases in our Markov chain simulations than Langevin where the system needs to ever take any corrective action, as opposed to only applying the highest voltage. But the policy seems to be effective in that it really drives the system back to this highly ordered state, and then we go back to our high voltage at the end. So in the Brownian dynamics, we do have some cases where at the end we're not in our highly ordered state, that we're kind of stuck, but we can see that the voltage here is continuing to go up, the average voltage, which means that we're not done, but we've gotten into a slower regime, and that's something that we need to understand in terms of our modeling. But this is an example of one of these unsuccessful Brownian dynamic control realizations, where we start off in this fluid-like state, we come down, and then at some point we cross this boundary of this condensed but disordered state, and we are kind of ratcheting over, but we're doing so very, very slowly. And so we need to probably refine the model in that regime to make the agreements between Langevin dynamics and Brownian dynamics a little bit better. But it does seem that once we take our Langevin model and we build the Markov chain Monte Carlo from that and do the control policy on that, it does actually agree quite well in the Langevin dynamics model. So that kind of affirms that loop, but probably we do need to refine our Langevin model a little bit. Another alternative is we can just build the policy directly from the Brownian dynamic simulation. And actually that's a kind of an obvious thing to do, and we've also been doing that in a different system. The problem is that the Brownian dynamic simulations take a really long time to run, so it can be nice to generate more samples to build a Markov chain model from Langevin than to do it directly from Brownian dynamics. But then it builds in this extra step of having to validate and refine the Langevin dynamics equation model. So whether or not that intermediate model is useful, I think is still an open question, or depends on the particular case. Now, we've been implementing this, working to implement this policy in the experiment, and one of the issues that we've come across is that it's really hard to control the exact number of particles. So this has brought up then the question of how robust is the policy to modeling inaccuracy. So we built the policy here for the two-dimensional case for 210 particles. So in the one-dimensional model with a different salt concentration, that was 130. This one is 210. So a first question that we asked then of the Brownian dynamic simulation is, what happens if we have a different number of particles? So if it varies by about 10%. So in this particular plot, we show that the average over 1,000 realizations for implementing the control policy for 190 particles and 230, as well as for the nominal 210 case. And what we see here is that it is actually pretty significant. One reason is that the radius of gyration is very dependent on system size. And so with the smaller system, it just has lower radius of gyration, so it crosses that boundary, sort of sooner than it should, if we were comparing sort of apples to apples and not apples to oranges. And so it ends up just down here hanging out in this low voltage input and really not being driven over into the highly ordered state. Alternatively, when we have a larger system, it's larger, so it's higher up on the RG plot, and it ends up actually crossing this upper boundary and then coming back into this, very undesirable state. So it's, again, difficult to precisely control the number of particles in these terms, but it's something that we can measure. So one question is, do we really just have to compute the policy for every particle number? But we'd like to not have to do that because it takes a lot of computation to just do all the runs in order to build the Markov chain matrices. Once we have the Markov chain matrices, computing the control policy with dynamic programming is not a big deal, but it just takes a lot of runs to get enough samples to build a Markov chain model for all 6 of those voltage levels. And so here again, we can see what's going on from a dynamic point of view, looking versus time. So basically, for the smaller and larger values of the number of particles, we end up with these low voltages that then just aren't ultimately taking us to where we want to be, like with 210. So one possible solution that we're working on is to rescale the state or input to account for system size, in a small range. Okay, so obviously the best thing to do would be to recompute the policy for every particle number, but we want to see, can we make some kind of correction? So we could rescale the RG values in the policy table based on the basically the size of the system, the size, radius of gyration for the condensed system or something. So we could rescale that. And then we also can rescale the voltage using the system size, because the Bevan group has studied the effect of system size here on sort of the minimum voltage needed to condense. So that also gives a scaling relation. You can see in this D plot here that these different data points for different salt concentrations and different system sizes, and they collapse onto this, different particle sizes collapse onto the same curve, and that gives us a way to rescale the voltage. So what we're going to do next is we're going to apply this rescaling to the policy and then apply it in Brownian dynamics and see if that allows us to get something better than this. So to be able to use our policy over a somewhat larger range without recomputing the policy. And then we can apply that rescaling in the experiments once we see how many particles we have in that particular run. Okay, so with that, I'd like to conclude. So I've shown here a demonstration of feedback, the proportional feedback control in a colloidal self-assembly system, and also our progress towards implementing optimal control in our colloidal assembly system as well. And I think that model-based control promises to optimize self-assembly, and so we're trying to get there to really do it in experiments. And stay tuned, it's underway. Now, you might also be wondering, would you really be doing this video microscopy in manufacturing? And the answer is probably no. But I think getting all of this information can really help us understand the ability to influence feedback control processes to develop better open loop strategies, or to use simpler, then be able to use simpler sensors, non-invasive sensors in a manufacturing process. So I just want to, I've already really mentioned my collaborators. I should acknowledge them again, like Bevan at Johns Hopkins and David Ford at UMass, and we have a joint grant from NSF that supports this work from the Cyber-Enabled Discovery and Innovation Program, as well as funding for the Bevan Group from AFOSR. So with that, I'd like to conclude and take any more of your questions. Thank you.
Okay, great. Thanks, Martha. Let's go ahead and open it up for a couple questions.
Martha, this is Jeff here. This is really fascinating stuff. I'm just curious about how many states are really present in the system. If you discretized size 6 in RG to say 100,000 nominal states, and if you were then to do some sort of system reduction on that, how many states would you think would be really necessary to model this thing?
Well, this is a really good question. And usually when people do this, they just do a grid, so all the states are the same size. But I think what is really important is what you want to make sure that over one time step, the system traverses several states. Because this model is really going to break down if your system over one time step stays in its same state, but ultimately, would be moving farther away.
Okay.
So I think it's really the relationship between the time step and the state. And so you could compute then, so it could be in certain regions of the space you can have really large states, and in others really small states. We also have some situations where we have a lot of free energy minima, different wells that are very close together in these highly crystalline regions, where you have a 1 defect and a 2 defect, and these are all very close in order parameter space. So resolving those, not having multiple of those wells in one state, is probably also important. So if you want to consider having sort of a variable mesh or whatever, then I think there are a lot of good questions there, and that's something that we're looking into more now, because it really has been kind of frustrating to pick the discretization level and the jump size and try to find something that agrees with Langevin. We have been able to get there, but we could, I think, really go back and look more into the theory of that and see how we could also contribute.
Well, I'm thinking, suppose you take your Markov matrix PA that you're showing in this slide, and you were to do a dimensional reduction on that. I think you might find states that are both big and small. Once you look at what states are included.
Yeah.
I'm thinking kind of like an eigenstates analysis on PA. How many states would really be relevant in the
right? I mean, you might be able to prove some aggregation of Markov chains is a kind of the area where I have been following or thinking about this, where you could go in and say, well, these states I can aggregate. So start with a very high dimensional state, and then say, well, really these are equivalent somehow, and then these can be pruned, and you could go through sort of an iterative process to try to reduce in that way.
Okay.
But it is something that you could really validate at the Markov chain level if you have a very high dimensional Markov chain, and then you could prune and compare and put it back in if it made a big difference.
Okay.
And I mean, there's so much opportunity for analysis of eigenvectors and eigenvalues, because it's linear. We're flipping back and forth between these 6 different Markov chain matrices. The A is denoting the action space.
Right.
And actually, in this, there's some really open, or maybe were open questions in terms of the validity of this model and of the Langevin equation in particular. And this is something that we dealt with in writing this control systems technology paper. That when you start with the original full high-dimensional stochastic system, and then if you generate the Langevin equation, it's really only for a constant value of the input. You're not allowed to have time-varying parameters, because the Kramers-Moyle expansion that you use in truncate and deriving the Langevin equation, and the Fokker-Planck first and then Langevin equation does not allow you to have a time-varying input. And so this is a real problem in using this for feedback control. So what we argued, and ultimately was accepted by the reviewers, is that because we're having these instantaneous switches, or modeling them as instantaneous, on this U-parameterized Langevin equation, it's valid. We're switching between models. We don't have a time-varying input. And so that's actually really important for the theory. But it's in this system, I think it is a good argument. It is valid, because we're using electrostatics to compute the effect of the voltage very fast in terms of, there aren't flow electrodynamics. So I think we can make the electrostatics assumption, time scale of maybe a microsecond, and it is legitimate. But if we can't change our input that quickly, then there are real theoretical questions in terms of this whole modeling approach.
Right.
So discretizing the action space actually was not just the hack that we needed to do the Markov decision process. Actually, it was essential in order to set sort of the validity of the whole dynamic modeling framework.
Right. I guess I'm kind of fascinated by the link between the Brownian motion model and the Markov model. And to me, the Langevin things would be an artifact of a dimensional reduction on the Markov model. But
yeah, the historical reason is that our collaborator Mike Bevan really likes the Langevin model. They like having the interpretation of free energy and drift in understanding what's going on and understanding the physics. So this is really something that they want to do kind of for other reasons. So that's sort of how it got in. In my past work in looking at crystal growth with kinetic Monte Carlo simulations, we went straight from KMC data to high-dimensional stochastic systems to Markov chains. So that's just very natural for us. But it has proven helpful to be able to generate more samples from the Langevin equation more rapidly. That actually is valuable from a practical sense.
Okay.
but then it brings in all of these, you know, all of these theoretical questions as well as additional sources of model inaccuracy.
Sure. Thanks.
Yvonne, do you have a question?
Yeah, probably, yeah. In this work, I just have the basic question. It's, are you using some Bayesian framework for the learning, the reward function in your inverse reinforcement learning?
We've thought about reinforcement learning. We haven't gotten there yet, but it would be a way to get around these modeling issues. So, and especially in the context of a manufacturing setting, I think it makes a lot of sense because all this model building is a lot of work, and then it's not always that accurate. So,
exactly.
I mean, it's pretty accurate. The Vevin and Ford groups have done a really good job of building these models, but in any case, if you could circumvent that, you know, that would be nice. So we're you know, long-term thinking about it, but we haven't started on it at all.
Yeah, I mean, because we are here in the group working with also a penalty function, and well actually we have a code for reward function, but then we decide just to go from making the constraints. Instead of using constraints, we start using penalty function, and yeah, we are getting some good results as we saw in your presentation, and it's really, really cool. But then I'm just, since I'm just starting masters here, I was just thinking about using Bayesian framework to include in the IRL. So I was just thinking if you have some experience with it, that probably I can read some of your papers about it. So thank you.
I don't, so I'm interested, but I don't know that I have anything to contribute specifically for you. In the past, I've really spent so much time doing sensor interpretation, estimation in crystal growth, and as well as very simple feedback controllers. So this project is really so exciting for me because we have all this data for feedback now that we can do, you know, dynamic programming. We can do model predictive control. So anyway, it's not an area that I've really been working on, but it's a direction I've been trying to move in. I'm happy to be finally getting there.
Okay, thank you so much for your presentation. It was really nice for me.
Thanks for your questions.
Okay, great. Okay, any last questions? I think we're about out of time now. So thank you, Martha, for your presentation. I thought it was very good and a lot of good discussion there as well.